afternoon, everyone, and welcome to AABC's Tab Talk webinar series. I'm Colleen McCain, Marketing and Member Engagement Manager with AABC, and I'll be your moderator for today's webinar. Thanks to all our members and non-members across the community for participating today, and a special thanks to IMI Hydronic Engineering for supporting this webinar. I have a few Zoom notes before we get started. If you have questions for our speakers, please use the Q&A button in your Zoom window, not the chat, and we will feed those questions to our speakers at the conclusion of the presentation. You can submit questions at any time. No need to wait until the end. If you have technical issues, please use the chat box to inform the panelists, and we will assist you. And finally, concerning AIA learning units, if you are an AABC certified TBE or TBT, please allow 7 days for your CEUs to be uploaded automatically to your portal. Today's session topic is hydronic balancing design flow at terminal units. Our experts joining us today are Soham Neupane from IMI Hydronic Engineering and Cody from Precision Flow Engineering. Soham Neupane is the hydronic training manager with IMI Hydronic Engineering North America. He's a mechanical engineer with a passion for connecting and sharing knowledge with HVAC professionals. Soham received his master's degree in mechanical engineering and has over 5 years of experience working in the industry. He has extensively worked with different types of systems, terminal units, controls, and balancing solutions for HVAC applications. Soham has been training HVAC professionals on hydronic products from a system solution strategy to help design energy efficient, optimized hydronic balancing and control solutions for their HVAC system applications. Cody is the president and owner of Precision Flow Engineering located in Mansfield, Texas. He has over 25 years of experience in the air and hydronic balancing as well as building systems commissioning. He is a licensed professional engineer in the state of Texas and holds a Bachelor of Science degree in mechanical engineering from the University of Texas at Arlington. Cody is also a licensed TBE and CXA. Founded in 2013, he and his firm quickly established themselves as trusted and sought-after tab and commissioning professionals, specializing in the healthcare, surgery, laboratory, pharmaceutical, defense, and petroleum industries. Now, I'm going to hand it off to Soham to get us started. Take it away.
Awesome. Thank you, Colleen, for the warm welcome and introduction. So let me share this slides here. Thank you, everyone, for
All right, everyone. Looks like we're having some technical issues. We are checking on it on the back end, and we will get started in just a moment.
Standing in a crowded room and I can't see your face. Put your arms around me, tell me everything's okay. In my mind, I'm running around a cold and empty space. Just put your arms around me, tell me everything's okay. Break my bones, but you won't see me fall. Oh, the rising tide will rise against them all. Oh, darling, hold my hand. Oh, won't you hold my hand? 'Cause I don't wanna walk on my own anymore. Won't you understand? 'Cause I don't wanna walk alone. I'm ready for this. There's no denying. I'm ready for this. You stop me falling. I'm ready for this. I need you holding. I'm ready for this. So darling, hold my hand. Soul is like a melting pot when you're not next to me. Tell me that you got me and you're never gonna leave. Trying to find a moment where I can find relief. Please tell me that you got me and you're never gonna leave. Break my bones, but you won't see me fall. Oh, the rising tide will rise against them all. Oh, darling, hold my hand. Oh, won't you hold my hand? 'Cause I don't wanna walk on my own anymore. Won't you understand? 'Cause I don't wanna walk alone. I'm ready for this. There's no denying. I'm ready for this. You stop me falling. I'm ready for this. I need you holding. I'm ready for this. So darling, hold my hand. Don't wanna know that feeling when I'm all alone. So please don't make me wait, 'cause I don't wanna break. No, I don't wanna fall. When you're next to me, content, I'm not afraid to be. You don't make me wait and never let me break. You never let me fall. Darling, hold my hand. 'Cause I don't wanna walk on my own anymore. Won't you understand? 'Cause I don't wanna walk alone.
Hi, everyone. This is Colleen McCain with AABC. Thank you so much for hanging on with us. We were able to iron out that technical difficulty. And without further ado, we have Soham Neupane here to go ahead and start our presentation for today. Soham, take it away.
Thank you, Colin. Sorry, guys, having technical difficulties. As you know, technology sometimes just doesn't want to cooperate. So let me do this again, share my screen. All right. Since I can't really see any of you guys, just making sure everything's good now. Can see my screen. Cody.
Soham, we still see that opening slide. If you just want to try and share your screen, the presentation,
Okay. Awesome.
you should
Do you
be
see
able
it?
to steal it away.
Awesome, thank you. All right, guys. So sorry for all the technical difficulty. So let's get started with the topic without any further delay. So since we're all HVAC professionals here today, let's look at why do we need HVAC systems, right? What's the objective of having any HVAC installation? So the first one, we want to ensure that we meet the specified design conditions, be it for comfort, be it for processes. Wherever we want to have precise control, that's what we want to achieve with our HVAC installation. And the second objective, which is equally as important, is to achieve the first one, ensuring that we have the lowest energy consumption. And we'll see why that's important that we think so much about energy consumption. And when we look at HVAC system, there are several different parts associated with it, right? There's the production side with your boilers, your chillers, there's your distribution, and there's your terminal units where your heat exchange is taking place. And it's important we kind of look into all that, make sure they're well balanced, and other aspects of it as well to optimize a hydronic system.
Soham, is it okay if I jump in here really quick?
Sure.
We're still not seeing your slides. If you want to try at the bottom of your Zoom screen where it says share screen, if you click on that, you should see options come up, and then you can choose your presentation. That way, everyone who's logged in with us can follow along with you.
Do you see the screen now?
Yes, perfect. Thank you so much. All right.
Thank you. All right, let's see. Okay. So yeah, what I was talking about is the two objectives of HVAC installation, right? So we want to meet the design condition, but we want to have proper energy efficiency, and that's very important. And when we look at human comfort in general, it's important to look at consider human comfort in general too, because just 2 degrees Fahrenheit deviation we see in the temperature can cause a reduction in human efficiency by 5 to 6%. And think of a building that doesn't have a proper HVAC system, an office building where you're going to spend 8 hours a day. You're going to feel tired, people will feel sick, and the overall efficiency goes down. So it's important with human efficiency, keeping in mind the human efficiency as well, that we have a proper HVAC system installed. And, going back to our second objective where we talked about energy consumption, why is that so important, right? So in the world, currently, 40% of the energy that's generated is being used in buildings. That's a huge number. Just think of it in, terms of United States, where there's about $3 to $4 trillion in energy spent in energy every year. And 40% of that basically is being used by the buildings. And 50% of whatever energy is in the buildings is being used by HVAC systems. Hence, it's very important we look at the system, overall system, and make sure that it works as it's supposed to and is not consuming more energy than it should. And when we don't really look into the proper design of HVAC systems, what we're going to see then is sick buildings, basically, right? So you're going to have huge temperature gradient, temperature fluctuations in your building. Some parts going to be too hot, some parts going to be too cold, and this will basically in turn result in what we call sick building syndrome. So some of maybe the first thing you'll start hearing is the system noise. So if there's like air and dirt in the system, in the pipe, and too high flows or too high pressure drop, you're going to start hearing noise, which no one likes noise coming out from up the ceiling, right? And similarly, you're going to see that all the dirt on the pipes basically gather. And I don't think this is a new sight for anyone here. You go to a job site, it's common we see that there are issues with like dirt accumulation and all that in a system. And then, we go further, there are operational risks. We're going to see a lot of energy fluctuations in a sick building. You're going to see instability of temperature and humidity. So that's going to cause user discomfort. And, at the end, your system would basically not operate like it should, and you're going to have the operational risk. And especially when it comes to critical applications, that's a major concern. And just, looking at system, it's very important that we take care of the system in general overall to make sure we avoid all this risk and energy consumption and unwanted energy waste, basically, because Just 2 degrees Fahrenheit too hot or too cold can cause energy consumption, more energy consumption up to 6 to 11%. So what do we do, right, to basically optimize an HVAC system? So there are three steps, basic fundamental steps we want to look at. So the first one is the power required at maximum condition. And that is what balancing is about. What we want to make sure with balancing is you have the required flow rate and the power that you need for your design condition throughout your system. And you do not want to spend any more than you need to. So you want to have just the right amount, but not overflow it, right? And that can help us save up to 35% just in pumping energy. So that's a huge number when you think of a building. You have hundreds of these valves installed there. Similarly, you know, when we start getting into partial load, we want to make sure we have good control in the system as well. So we operate at less than 50% load for 80% of the time. And that's basically, you know, responsible for a large amount of energy consumption. So we want to have proper control valves selected, you know, proper control mode selected. Just using on-off system versus a proportional can basically consume 7% more energy overall in your HVAC installation. And the third one is, you know, looking at even further out in the system where we want to make sure we have the right static pressure, we have the proper degassing, you know, air and dirt separators and all that, because those pipes, the pictures we looked at earlier, if you have 1 millimeter of dirt on your pipes, that can result in up to 9% overconsumption in pumping energy. So, you know, it's important we kind of take a look at the system overall and kind of understand what we need to do to make sure everything is working, not just working, but working efficiently, right? And before I kind of get into this, today we're going to focus mostly into our power required at maximum condition. That's the design flow. And when we don't have that, we don't have proper balancing, what happens? We overflow, right? So why worry about the overflow? Because what you see, you know, we hear this a lot in our ASHRAE conversations and journals, and, you know, this is a topic of interest where you start seeing low delta T issues for your chillers mostly. So just for an example, you know, say you have a heat exchanger basically with 10 GPM design flow and a 40-degree delta T. What happens when we start overflowing? Say instead of 10, now we're overflowing it by 50% and you got 15 GPM going in. And the delta T now is basically reduced to 20 degrees. And say, you know, with the circuit even is further overflowing because we didn't have proper balancing solution installed, what's going to happen to the delta T now? It's down to 10 degrees. So 180, 170, from 180 and 140 that we were originally looking at. So you see this big impact on the delta T, thus, you know, it's going to affect the performance of your chiller and boiler and all that. So when we look at a chiller, this is a simulation which was done for, you know, 200-ton chiller with 85-degree and 95-degree condenser temperature and a supply temperature of 45 degrees. So when you look at this chart here, so if the return temperature of this was set at 54.5, we had a coefficient of performance. I mean, we want a higher coefficient of performance for our chiller to be more efficient. So our coefficient of performance was 5, and you see just about 1 degree lower delta T can reduce that efficiency to down to 4.6. And from 54.5 to 51.08, you see that there's about 15% reduction in the coefficient of performance of the chiller. So your chiller is now not as efficient and will be consuming more energy. And it is one of the major consumption of, major source of energy consumption in any HVAC system. So basically what happens is, you know, when we overflow in your coil doesn't spend as much time in there. So there's not much heat exchange happening between the coil and the air, between the water in the coil and the air. And as a result, like, you don't see that big change in the temperature of your water. And that's the reason you see the delta T issues. And, you know, when you look at chillers, what happens is so the chiller was, if it's designed for 55 degree and 45 degrees here, for your return. 45 and 55 degrees. So what happens is as your return temperature lowers from 55 down to 52, your evaporating temperature on your refrigerant lowers automatically, which then will lower the overall efficiency of the chiller. And that's what we want to avoid. We do not want to see that lowering of the coefficient of performance in our chillers. So some of the main reasons, right, that's causing this, let's look at those. So the first one is three-way control valves. So, like diverting circuit with constant flow, which was more common in the past, not as much now, but that's one of the main reasons you see on for delta T issues. So what happens is you have a bypass. So the delta T basically increases when flow reduces. So, if you are sending less water into the coil, it's got to spend more time to heat or cool your air. So you're going to see increase in delta T. But in this case, since we have a bypass here, what's going to happen is if we don't want that flow here through the coil because it's going to be variable, we're going to bypass that water from this bypass, the rest of the extra water. And what happens, say we do not want any flow here in this coil, we're going to bypass everything from this bypass. So all the water is going to go through the bypass. And what are you getting? You're not getting any delta T at all. Whatever you're getting in your supply is basically going back to your return. And that's not good. In that case, your chiller's just going to do more work. And, same thing, even if it didn't close completely and you had some water bypassing and some water going through the coil, you'd still have the same issue with a higher temperature water, with a lower temperature water mixing with a higher temperature water. And then that's going to affect your delta T. Okay. So we want to avoid that as much as possible because, last thing we want is our chiller not performing as it's supposed to and having to maybe add a more chiller in the future or, just have a very non-energy efficient system. So moving on, another reason, second reason that causes your delta T issue is basically your supplier temperature depression. So what happens is we see that, especially with the maintenance people on site, what happens sometimes is when we're not able to get that room temperature real quick, people just tend to switch the set point. So you lower the set point that you have. And what happens, see, if your set point so to reach your set point, initially the system was designed with 55-degree leaving air temperature and 16-degree delta T. But as we keep lowering that set point, you see from 55 down to 52 and 50, you see that big change in your delta T values. So as we change the set point, the delta T on your chiller is also getting affected at the same point. Similarly, the third reason here, again, for a delta T issue is warm chill water supply. And this is a pretty common issue too. Again, it is a general notion, I would say, that, okay, if I change my set point of the chiller, just make it a little higher, I'm going to save some energy. But that's not exactly what happens. So when you go in and you start changing you basically start warming the chill water supply. What happens? So initially it was at 42 degrees with 16-degree delta T. And you increase that temperature by 5 degrees, you see the delta T is more than lowered, lowered by more than half. And then, you increase it further, it just keeps getting worse. So we want to avoid that as well. These are the three reasons. And the main reason, which I kind of saved it for the last, which is what we're going to focus on today, is unbalanced system, right? So unbalanced system, again, if it's not balanced, you overflow your system, your water does not spend as much time in the coil, and you do not get enough delta T, and hence it's going to affect your chiller performance. So this curve here, basically, actually, let's start with this picture here. So what happens in unbalanced system, then because you're overflowing and all, you're going to see the temperature gradient that I was talking about. Closer to the pump, you're going to have higher temperature and much lower temperature up top. And with overflow, you are also wasting a lot of energy, not just chiller, but also with pumps and all, right? So this chart here is from ASHRAE Handbook from 2019. So what it shows is your characteristics of a typical heat exchanging device, heat exchanger. So the way it works, as you can see, it's not a linear curve, is you increase your flow to 200%. So 200, double the design flow. What you see is only 6% increase in heat transfer. You see the big difference from 100% flow to 200. So you're pumping twice as much water all the time in your system, and all you're getting is 6% higher heating or cooling output. And that's a lot of energy being wasted for something that's not even basically not even enough to make you feel any kind of changes. But in the background, you see you're wasting a lot of energy pumping that water. So that's exactly, we want to avoid unbalanced system, and we're going to deal with that today and look at what are the ways we can properly balance a hydronic system. So let's dive into more detail of balancing and different ways to balance them. So balancing the water flow rate, right? It's important, as we said. Water's lazy, it's going to take path of least resistance. So when you have a system like this, where you don't have proper balancing and you just have control valves, say, what happens? You look at this circuit closest to the pump, that's the easiest to satisfy. So your water is lazy, it's just gonna go, most of the water is just gonna go through this supply, come back through that return. And the farther you go, there's more pressure drops you have to come over. And thus you're just gonna have less and less water, and you'll start underflowing at a certain point downstream. And that exactly is what causes this temperature gradient in the building. People who live closer to the mechanical room is very hot and sweating, whereas people living like up top is probably freezing. So that's something we see commonly when a system's not properly balanced. And that's because you do not have a good differential pressure distribution. And you have high differential pressure closer to the pump, you overflow the circuits, move further, lower DP, you underflow the circuits. So some rooms are too hot, some rooms are too cold, and control valves just cannot solve this issue. You do need balancing valves to be able to not overflow your system and balance it. Okay, and with balancing, what we are doing is we are basically restricting the flow in the circuits. So now, since control valves were overflowing and underflowing, we go in, we add balancing valves in here. So what happened is, what we're doing is we're adding resistance on each of these circuits, wherever we're adding the balancing valve, to make sure that we do not overflow. So we just have the right amount of resistance you need to make sure you get the flow that you are for your design condition. And that way, what happens is the differential pressure distribution through all these units, assuming that therefore the same flow, is going to be more or less constant. So this differential pressure is going to be constant, and as a result, you'll not see overflow and underflow, and you'll see more even distribution of temperature throughout the building, which is exactly what we want. We want to avoid the gradients as much as possible. And thus we want to focus on balancing and make sure we have proper balancing solution installed in the buildings. So what are different ways of balancing, right? So let's look into that. So there are two widely used ways for balancing. And the first one we're going to look at is static balancing, which is also known as balancing with manual balancing valve, right? So this kind of balancing solution is ideal for low thermal load fluctuations, where you're not going to see high changes in the thermal load at all the times. And it's also great for any general thermal comfort application for your hotels, hospital, commercial buildings, you name it. And of course, we'll not talk much about potable water today. We'll not talk about potable water at all today, but it is important, your recirculation system as such in a building is properly balanced as well. And there are various ways to do that with manual balancing solution. So now let's look at this manual balancing solution in a little more detail here. So this is the formula, how we calculate the flow of on a given balancing valve. So CV is basically the opening that you have on your valve. Your delta P, the differential pressure, is the pressure that you measure through that PT ports. And since we know whatever CV we're picking for the manual balancing device and the delta P that we can measure, we're able to calculate the flow. So let's take an example here today. With a system, we've got a chiller, a primary pump, we got secondary pump, and we've got 4 circuits here with fan coils. And we've got bypass and all built in as well. So, it's a well-designed system. And we're gonna consider some pressure drops here. So let's say we've got 1 feet of pressure drop in this piping in each of these circuit. We've got 4 feet of pressure drop on the fan coil and 5 feet of pressure drop on the control valve. And we've got 1 feet of pressure drop basically on your supply and return distribution pipes here. Okay, so remember earlier we talked about how with manual balancing, we're adding the right amount of resistance so that we have the equal differential pressure throughout the building, right? And that's exactly, we're gonna see how we do that. So let's look at our first circuit with fan coil 1. The total pressure drop that you have on here is 10, right? So we've got 1 feet on the pipe, 4 feet on the fan coil, that's 5 total, and then 5 on your control valve. So we've got 10 feet of pressure drop. You go to the second circuit, we have the same 10 feet on this circuit as well, plus we have additional 2 feet that we have to go through, right, in our piping onto the second circuit. So we go to the third one, you add 2 feet more of pressure drop here, and that basically gives you 14. And you go to the last one, we've got 2 feet more, that gives you 16 feet of pressure drop. So now what we'll start doing is, we just have a system that basically has variable pressure, as you can see, pressure drop, and there's no balancing added to it. So now we're gonna go and place some balancing valves in here. So once we do that, how do we select the right balancing valve, right? How do we know the resistance we need? So 1 feet of pressure drop is what you always want to design for in your index unit. So when I say index, that's the hardest to satisfy. And in this circuit, it's going to be your last one. So what we want to make sure is we have minimum pressure drop on this index unit, because if we size this for a higher pressure drop, we're going to have higher pressure drop in all of these valve upstream, and we'll look at why. So as per ASHRAE, we want to have 1 feet of pressure drop on our index unit. So that's what we size this valve for. We have 1 feet of pressure drop on that manual, with that manual balancing valve added to the circuit. That gives us a total pressure drop of 17. So now we know that we have total pressure here of a differential pressure here of 17. And what we'll start doing is to stabilize, to have that equal differential pressure in each of these, 1, 2, 3 as well. We're gonna add just the right amount of resistance to get to that 17 for our differential pressure. So now what we'll start doing is we'll add just the right amount of resistance we need to get to that pressure. And that's how we're basically able to, with the manual balancing valves, we're basically able to get equal differential pressure in your system, and thus kind of, take over that risk of overflowing or underflowing your terminal units, okay? And as I mentioned, it's based on what valve you're picking. It's the CV of the valve. It's the opening that you have on your valve and how much you restrict it. So, the closer you get to the pump, the more restrictions you're going to add, of course, because you want to have higher pressure drop. You need higher pressure resistance closer to the pump, because that's where you're possibly going to overflow. So, it's just going to be more closed as you get closer to the pump. So let's look at this quick clip here on manual balancing. So any building, we've got your supply, you've got your return, and that connects to your heat exchanging device, right? Your coil for your comfort to each room. And it could be balanced using manual balancing valves. So you'd have manual balancing valve on all the terminals. And those valves are adjustable and flexible, but it's static. So when I say adjustable manual balancing valve, it can be set for different flow, because you have a handle that can adjust for different flow. So it has a range it can control. Whereas the only thing with manual is it's static. So it's not going to adapt to any pressure changes in your system. It's not reacting to any pressure change in the system. And all it is doing is basically limiting your flow and nothing else. It's setting the max flow limit for the valve. So now when we look at a typical installation in a building, this is how it looks with a manual balancing valve. So You would have a manual balancing valve on each terminal unit, and you would have a manual balancing valve on each branch and a riser and close to the pump as well. So the valves, these manual balancing valve on each terminals, that's pretty standard, known about, right? And partner valves, something we encourage, is very necessary for balancing, because with manual balancing, you have to make sure we balance the system. It's not self-balancing, so we have to make sure proper balancing is done. And partner valves are very important to ensure that we can properly balance, and we'll look into that in more detail later as well. But we want to have partner valves installed on each branch, riser, and closer to the pump. And that's a typical layout you see. And balancing with manual balancing isn't that easy. If you could kind of think of, what comes into play is the interactivity. So think, you've got a system, you've got a hose basically that's connected to a common water outlet, and it has several outlets basically, and we all are holding the hose, the outlet of the hose. So if I go in and turn on the water, we all will start seeing the water flow, right? And that's the design condition. But what happens is, if someone else closes one of the outlet, what happens is you'll see more water coming out of the rest. And that's interactivity. So when something in the system changes, you're going to see that affect the other parts of the system. And it makes it difficult, because as you go and adjust one, it's going to change the rest and all. So it's important we develop proper understanding of balancing and how we can balance to make sure our building's properly balanced and we're not overflowing, right? So let's walk through this example here together, and we'll look at this example plan here. We'll simplify it. It's a multi-story building that we're looking at. So we'll simplify it and work on it together to see how we can properly manually balance, okay? So the way to do it basically is by creating hydronic modules. And when I say creating hydronic modules, what we're doing is, we talked about partner valve. So with the partner valve, when we have a partner valve going into this main, like your distribution pipe, and you have several other balancing valves downstream, what happens is this whole thing starts working as one unit. And what it does is it helps us use the proportional rule, which I'll explain what it is later. And that basically helps us make the balancing process much easier and work independently in modules and optimize the pump as well. So let's get started and see how we create modules, okay? So this is just the simplified version of the drawing you saw, the plan that I showed earlier. So, simplifying is important. It's just easier, much better for us to look at. So once we do that, we start basically placing manual balancing valve to create modules, okay? So what we'll do is we'll place a manual balancing valve by the pump. So that's the first manual balancing valve we place by the pump. And then we'll follow the pipe with the main flow, and every takeoff, we'll place a manual balancing valve, okay? So we do that again. At the takeoff, you place a manual balancing valve. One thing to note is that if there's only one terminal unit and any of those takeoff, just know that that's not your partner valve, that's just your manual balancing valve. We don't need any more manual balancing valves there. But if there's more than one terminal unit, then it's a sub-module. So what we're doing right now, where we place this valve, because there's more than one terminal unit, that is now a module. So this is now a partner valve, and we know that we need to go into these sub-modules and start placing manual balancing valves in there, okay? So for that, few things we need to kind of keep in mind is the turning direction when we look at creating hydronic modules. So any kind of bifurcation between many and many units, you want to turn towards the direction of the main flow. So wherever you have high flow, that's where you want to turn. And on any bifurcation between one and many units, so that's one terminal unit on one side and several on the other, you always want to turn towards the side with many terminal units, regardless of the flow. Even though this GPM is higher, I want to go towards where more terminal units are. And that bifurcation basically, could be your vertical T or horizontal, so that doesn't really matter. So let's go and start placing those valves on our simplified plan together now, okay? So as I said, we'll start with the pump. So close to the pump, we already have a manual balancing valve. The purple ones are my partner valve, okay? So this is our main module. So we start moving up on the module. And now we reached a takeoff here. So, I've got one terminal. So I know that's the final one. So I place a manual balancing valve and I'm marking this with red just to kind of differentiate that from a partner valve. So I place a manual balancing valve on each of these terminal unit. And then I get back on my main line, move further, got one terminal unit, place your manual balancing valve. So we follow the line again, the main flow. And again, we've reached a bifurcation. So what direction do we go? So we have many and many units. So we want to go towards direction of main flow, which in this case, you have so many units up top. So it's going to be that way. So what we're going to do is we're going to place a partner valve to the right and follow the direction of the main flow. And now we've reached another point here where we need to place a partner valve, right? So again, we've got many units on one side and many units on the other. Let's say this is where most of the flow is going since we have more terminals on this side. What you would do is you'd place a partner valve over here and then follow the main line again. And same thing here. Again, you have a partner valve going into these terminals. And each of these, as you can see, are individual terminals on there. And we place manual balancing valve on each of them. So now we basically have a placement of some manual balancing valves, the final ones, as you can see in the red on your terminals, and partner valves installed, right? So now let's look at submodules. So this is our first submodule. So I would go in, follow the direction of the flow, and I would start placing manual balancing valve on each terminal unit. So now our next module is right here. We do the exact same thing. So you go in, start follow the direction of the flow, start placing your manual balancing valve. And then we go to our third module, same thing, follow the direction of the flow and place manual balancing valve on each terminal. All right, so now what do we have is basically a floor with one main module and three submodules. And this method of creating these modules is very important just because it helps us to balance the plant systematically and kind of independently from each other. So, you can balance in sequence while a part of the project is still being built. You can start balancing the other part and have not to worry about the changes it's going to make to your existing part of the system. So earlier, if you guys remember, I said we want partner valve to make balancing easier. And that is by exploiting the proportional rule. So what's the proportional rule for balancing? So when we have a partner valve, right, that we looked at earlier, and this, for example, let's say we have 100 GPM here, and we have 30, 20, 10, 20, 20 GPM going in there, right? So the proportional rule, what it says is, what if we have a partner valve here, whatever changes we make on this valve, the flow downstream is going to change in the exact same proportion, okay? So say we have 150 GPM going in here now. So what happened is that you saw 50% increase in the flow here on your partner valve. You'll see exact 50% increase in the flow rate in each of these valves in your terminal as well. So that's great because now they are all proportional. So if I lower this down to 100, all of these will go down by 50% again and have that kind of get back to this exact same flow rates that you see. So that's the proportional rule, which kind of help us create these independent modules, even using manual balancing. So if you have changes, say you have a system, you have a building which has phase construction going on, what we can do is you got your partner valve, you've got your terminal units. So now what you can do is you can basically balance this. And what we're doing with partner valve is making this kind of independent of the changes from the rest of the system, because all that is going to affect your partner valve, and all this works as a single unit that we can control. So simply by throttling our partner valve, we are able to basically, control the flow by exact same proportion on each of these, rather than having to go to every individual one of these. And think about hundreds of them on a job site, right? So now, you're able to do phase constructions for each of these risers here, just because we have partner valves installed. So it's important, to kind of understand the rule of proportionality and make sure that we use it to balance. And as I mentioned, not balancing is important, of course, but we want to make sure we have the right amount of pressure drop for balancing. So that ASHRAE rule I mentioned with 1 feet of pressure drop or 0.5 psi. So that's kind of what we want on our index circuit. And that will basically define what pressure drop you're going to have in everything upstream, right? So if we have a higher pressure drop on the index, you're going to see you'll need much higher pressure drop on your circuits upstream too. And this basically, helps us save on pumping energy, because when you have properly sized the valve, we got 6.4 psi pressure pump head here in this system. Whereas, even if the system's balanced, but you are not doing it properly with the right pressure drops, you're going to see much higher pump head that you need in your system. So it's important we kind of understand all that, because not just balancing, but also the importance of pressure drop and all. So that's basically, manual balancing, and I hope that kind of clears out on, why it's so important to look at balancing procedures and pressure drop when we are doing manual balancing. And with that, I'm going to go to our second solution, which is dynamic balancing, also automatic balancing. So this is good for, high thermal load fluctuations and for any kind of general thermal comfort applications, of course. And let's kind of look at how is this different from manual balancing that we just looked into so much detail, right? Okay. So if you remember, this is the typical layout of your manually balanced building. You got manual balancing valve on each terminals, then you've got partner valves on your branch, your riser, and closer to the pump. So what we do different with automatic balancing is you eliminate the need of all these partner valves. So when you're using automatic balancing valve, there's no need to have any valves on your branch, riser, on your branches and risers. And the way it works is basically when you have a system, you place automatic balancing valve on each terminal unit. And, it's easy, it self-balances, so it saves time, but it lacks the adjustability. In manual balancing, you could change the flow rate, whereas in automatic, you really can't. But the biggest advantage here is your pressure independence. So automatic balancing valves are pressure independent within a certain range. So that kind of takes care of that interactivity piece. So you don't really see, the other parts of the system affecting the part you are actually currently looking at. So you're working on one automatic valve, no matter what other part of the system is doing, it's going to regulate that flow. And what autoflow is basically doing, automatic balancing is basically doing is, it has this cartridge kind of mechanism that changes the opening of the valve, and it adapts the opening, this opening right here, the CV, to fit the differential pressure and the flow to make sure that you always maintain that constant flow. And while on operation, this is what it's kind of doing. So when you see some pressure changes, your spring is either going to retract or contract there. And then, depending on pressure change, it's constantly adapting the opening. As you can see, the CV keeps adjusting and ensure that you have that set flow despite the pressure changes. And that's how it takes care of interactivity, okay? And when we look at this in a chart, this is how it looks like. So we've got flow versus your pressure drop. So when your delta P, where differential pressure is too low, your valve will just really won't be doing anything. And as you reach that pressure range where the valve is supposed to operate, and 2 to 32 PSI or 5 to 60 PSI is the most common pressure ranges we see. So depending on what pressure range you're using, within that pressure range, it is going to maintain that constant flow regardless of changes in the system, and you have no interactivity. And anything above that, you're just going to overflow, right? Your spring is not going to be able to take care of it. So with this, solution, the biggest benefit we see is in retrofit projects too. Like, when you have to expand or change an existing system. So say you have a building and you have a new portion that you're going to add to it. So with automatic balancing, first of all, you do not need to balance. They self-balance and kind of make sure that you have the water flow everywhere, so it adapts to your differential pressure in the system. So there's no need to rebalance. And whenever you make that addition, you do not really need to worry about what happened to my existing part, because it's not going to be affected at all, because there's, you're not going to see any interactivity. Okay. And, that's automatic balancing solution basically in a nutshell. And manual balancing, which we looked at as well. So those are the two widely used balancing solutions out there in the market. And I hope, this presentation today kind of gave you guys a little more insight on each of those solutions and how they work. And, regardless of what balancing solution is being used for a project, our goal here at IMI Hydronic is to deliver optimal performance. And we don't just want to look at, a particular product or a solution, but, we want to support you as a system using various tools, resources. We have been working, we're experts in water-based HVAC systems, and with years of experience and expertise in not just the solution, like the products and solution, but the system in general, we are committed to provide, like the best return on investment and energy savings with all the product. IMI, as you can see, is a larger group. We work on flow control. IMI Hydronic, we focus on HVAC water-based solutions. And, we have been doing this for over 30 years. And over these years, we have developed several tools to support our customers, of course. So, you look at selection softwares, or operation costs, we can even look at different solutions. So today we talked about two different solutions. We have ability to look at different solutions for hydronic systems, kind of do a comparison of, two, three different solutions on operating cost, installation cost, commissioning costs, and whatnot. And, other tools for measurement, be it for conversion, calculation, or just simply, selecting the valves or pipe sizes, you name it. We are able to support you with that. And this has all been, we have been able to do all this through, our great supportive team from Hydronic College. We do a lot of trainings here in North America as well. We have trained over 500,000 customers since 2004 through Hydronic College. And we have training centers here in North America too, where we can host trainings on hydronic systems and can have hands-on immersive experience with all that. And engineering support center, which I really like to mention, is another service which basically, looks into your design, your system design, looks at your pipe size, your valves, takeoffs. We look at your pump. We can do like full hydronic calculation to look at the position of your, DP sensor, or what's the set point and the pump head and all that kind of good information, and make a recommendation based on that, based on our experience and expertise working with this. So I hope this presentation was helpful and you guys are able to take something useful for you in the future for your project. And with that, I've reached the end of today's presentation, and we'll get into the Q&A session here with Cody.
So much, Soham, for the presentation. Due to some technical difficulties at the beginning, we're now going to run the IMI Hydronic Engineering video once again. All right, and that leads us right into our Q&A session. Cody, I'm going to kick it over to you to get us started with any questions that came in or any questions that you have for Soham about the presentation.
Okay, Soham, first of all, thank you very much. That was very thorough. First question I had, that early in the presentation, you bring up 2 degrees Fahrenheit correlates to roughly 6 to 11% loss in efficiency. In your opinion, is that due to just facility operators knee-jerk reaction, changing set points, or changing settings, or manually changing equipment? Is that what that's due to?
It could be for a variety of reasons, Cody. So, just kind of not having a properly balanced system could be one. Not having proper control system could be one, where, if your control is not properly sized, then your control valves are probably hunting, and whatever set point you set at, you're always trying to reach that, but you will never really hit the number. And that's where you start seeing this, basically fluctuation in the temperature, either, a degree higher or a degree lower. And that basically starts causing comfort. So I would say it's like a combined effect. There are different aspects that kind of, starts affecting that temperature control. So, it's balance. It's not just balancing or the maintenance guy. I mean, it's the system in general, what kind of control you've got is your system properly balanced,
Understood. Colleen, would you like me to handle the Q&A, or is that something you want to do?
Questions that came in from attendees. So I can go through the few that came in, and then I can kick it back to you if you have some that you'd like to ask Soham.
Okay.
All right. The first question here that we received says, does automatic balancing need to follow 5D rule during install?
For automatic balancing, no, you do not have to worry about the 5D rule.
All right, and the next question is, does proportional rule for balancing apply if one of the valves were to be closed?
Yes, that's a very good question. Yes, even if one of the valves were to be completely closed, if you have a partner valve, the proportional rule automatically applies to all the valves downstream. So you're still going to see that proportional increase or decrease in the flow simply by using your partner valve.
Okay, thank you. Next question, what is the difference between static and dynamic balancing valves in hydronic balancing?
So when we say, static and dynamic, just by the term itself, I would say static balancing is manual balancing and we call it static because it's not responding to any kind of pressure changes in the system. So, that's why you see interactivity. So if the valves in somewhere else in the system stops closing, you're probably going to see some more flow going through that valve, right? So that's the static balancing. Whereas when we start looking at automatic balancing, we call it dynamic balancing because it has a dynamic moving part, right? We looked at that cartridge with the spring. So what it's doing is it's constantly adapting to your pressure change, changing your CV, which is the opening, which is why we call it dynamic balancing, because it's constantly dynamically adapting to the pressure change. Whereas with manual balancing, you set a valve with a fixed opening and that's what it stays at. I hope that kind of clears out the difference between static and dynamic.
Thank you. All right, next question. Could the use of pressure-independent control valves avoid the hydronic balancing process?
Yes, so pressure-independent balancing and control valves usually do have balancing kind of built into it. So with those valves, you are able to set your maximum flow through each of your circuit. So yeah, you do not have to look for a separate balancing strategy for the entire solution with a pressure independent balancing and control valve, as long as we are able to set that max flow rate with the balancing portion in that control valve.
All right, thank you. I understand here we've gone over time just a little bit, but I do see many of you have stuck with us. We're going to go ahead and continue the Q&A for a few more minutes. All right, Soham, the next question. kind of a long one. On many automatic balance valves, the ports are very small and are subject to plugging up or fouling, so they don't operate properly with scale or sludge. I think they work great in a lab environment where systems are perfectly clean. But what about in real life systems that are less than perfectly clean?
Yes, so with automatic balancing, there are concerns we do hear concerns with the clogging, like mentioned. Of course, I think, we do need to start looking at taking better care of our systems, especially when we look at retrofit. Just the dirt and air that's in there. I think that's kind of what we need to start looking into and having proper design for that too in the first place. But if we already have a system like that, also, it really depends on what kind of design we're using. So, there are several types of automatic balancing design, which I'm not going to get into more details because that would be a whole another session. But, you've got certain designs with diaphragms and, you've got cartridges and such. So really, depending on the porting, how those ports are being made on automatic balancing valves, we are able to overcome that challenge. And we have done it with, automatic balancing solutions. We have seen that where, whenever you have a certain design, say like a diaphragm type of design, you're going to see easier clogging and probably much faster failure of the product. Whereas, when you have like a more like a stainless steel cartridge with larger porting to avoid that little opening where mostly, all these dirt and all will go and clog in. That kind of helps overcome that. And then, I think the sound and all, if there's air in the system, you're going to hear the sound, of course, but just those little things, with the system we need to take care of and understand with the product or the solution that we are using would definitely help overcome that.
So just to expand on that a little bit, it's not universal, of course, but we have seen on projects to where if you're clogging the automatic flow device, then you're not all that far from clogging the manual balancing device as well, if not out and out clogging strainers. There's not that big of a difference to get there.
Yes. And you always have a control valve, which is going to have even like a smaller opening. And that's possibly where you're going to see that happen more than, your balancing side, I would say. So it really just depends on the system. And as I said, it's important that we kind of make sure that, that the system itself has proper like air vents and proper like dirt separation in there.
All right, thank you. Next question. How would the installation of a VFD on the main supply pump affect your balancing? Is it recommended?
Constant head kind of solution is recommended for balancing. With VFD, it should not really affect, we're talking about manual balancing at the same time. It shouldn't really affect the whole balancing procedure, but what I would say is like a constant head constant head for the pump is preferred for balancing for sure. Better balancing.
Okay, next question. Do I need a balancing valve even with advanced controls with modulating control valves?
Yes. So, we talking about control valves, control systems. There are certain delays you are looking at with the response time with your controls and all. So, not your control system basically cannot take care of all the changes you're going to see in your system. At the same time, if you're not balancing, when you are at partial load, it's okay. You're dialing down the flow, but then imagine your control valve starts opening, then all of a sudden you start overflowing the circuits. So as soon as you overflow a circuit, you're most possibly underflowing some other circuit. So it's really important that balancing valves are used with control valves, because control valves in general are oversized as well. They aren't really sized for the location they need to be at, but they're kind of more or less sized for a certain DP, I would say, differential pressure. And that basically does not help us with limiting that flow or anything like that. And you are still going to have issues without balancing.
All right, thank you. I do have one last question, but Cody, I just wanted to check in with you if you had any other questions for Soham before I hit this last question.
No, Colleen, go ahead.
Okay, perfect. All right. Last question. Please explain bypass flow when a bypass is included, but no GPM is specified.
Cody, you want to add something to that?
It's a pretty broad question. I think I know what the person is referring to. We don't see, obviously, three-way systems are going away. I can't remember the last one I saw one on a plan and spec project. To answer a broad question with a broad answer, it depends a lot on where the bypass is located. Obviously, if it's located in the plant, I'm talking strictly about chill water. If it's located in the plant or far, far out at the system, say at the end, again, talking chill water, you need to know straight off the top what the minimum flow for that chiller is. And I would use that as a target number. And sort of by hook or crook, find a way to get the system at absolute minimum flow and set the bypass that way. If you are seeing an old school, I'll call it three-way system, the way to set the bypass basically is to have the ability to manually switch to bypass mode. And at that point, set the bypass to exactly what the design GPM for that coil is, or heat exchanger, or whatever the medium is.
Yes, and just to add to that, and we want to make sure it's for that flow, and we want to make sure that the differential pressure, basically what you're reading on a bypass, is same as the differential pressure across your balancing valve on your return side when you're doing that on your terminal unit.
Right, and also if you are encountering a lot of bypasses in the drawing phase, you need to pay very close attention to where the valve is in the bypass, or even if they have one. The handful of bypasses we've encountered on new construction in the last, say, 5 to 7 years, didn't even have a valve in the bypass. They just had I call it naked leg in there. And that's problematic to try to balance. I mean, really, you can't. The diagram you showed on your slides was the correct way to set up a three-way system.
All right, thanks everyone for sticking around through the extended Q&A. We had some really great questions, so thank you for submitting those. And I'd like to thank IMI Hydronic Engineering again today for supporting this webinar, as well as Soham and Cody for lending us their expertise today. A quick reminder, if you are an AABC certified TBE or TBT, you will receive the AIA Learning Unit certificate to keep for your records within 24 hours. But please allow 7 days for your CEU credits to be uploaded automatically to your portal. Tab Talk webinars will continue in 2022, so be sure to stay tuned for upcoming registration opportunities. And on behalf of the AABC team, I'd like to wish everyone a happy and healthy Thanksgiving holiday. Thanks for joining, and we'll see you next time. Bye, everyone.